All right, welcome to this video where we're going to talk about the relationships between pressure, volume, and temperature. And so we're going to talk about what happens to pressure if you increase the temperature, what happens to the volume if you increase the temperature, and what happens to pressure if you increase or decrease the volume. So we're going to talk about the relationship between those three variables. So we're going to take a look at the simulator here. We're going to put some gas inside of the simulator. Here we go, we're pumping some gas in there. And if you take a look, we've got our pressure gauge right here. Okay, here's our pressure. It tells us the atmospheres of pressure. We've got our temperature here, and obviously we can see the volume. All right, and the volume you know can change and all that. So the volume can increase or decrease or whatever. So what we're going to do is when we're looking at these different relationships, we're always going to hold one thing constant. Because when we're talking about, for example, pressure and temperature, we're going to hold volume constant. Whatever variable we're not talking about, we're going to hold constant. So we're going to start off by holding volume constant. What that means is the volume, the amount of, or the size of the container is not going to change. And what we're going to do is look at the relationship between pressure and temperature. So what happens if we increase the pressure? So I want you to ask yourself this. I want you to answer this question. What is going to happen to this pressure gauge if we increase the temperature here? So I'm going to add some heat here. What will happen to the pressure? Will the pressure go up or down? So let's go and take a look. We add some heat energy, the pressure goes up. If we cool it off, the pressure goes down. This is called a direct relationship. A direct relationship means as one goes up, the other one goes up as well. As one goes down, the other one goes down. So if you increase temperature, you're going to increase pressure as well. All right, let's go ahead and look at the relationship between temperature and volume. And so what we're going to do is hold pressure constant. So we're going to hold the pressure constant. And what's going to happen to the volume of the container if we increase the temperature? Is the volume of the container going to get larger, or is it going to get smaller? So we're going to increase this here. So ask yourself this: will it get larger or will it get smaller once I increase the temperature? And here we go. Look at that, it gets larger. If you increase the temperature, you will see that the volume gets bigger. If you decrease the temperature, the volume gets smaller. And so this also is a direct relationship. As one goes up, the other goes up. As you increase the temperature, you're increasing the volume. And hot air balloons come to mind. So the hot air balloon gets inflated because they put hot air inside of the balloon. Now the last relationship is volume and pressure. So we're going to hold temperature constant, and what we're going to do is we're going to change the volume. What I'm going to do is I'm going to make this container smaller, and what I want to ask you is what's going to happen to this pressure? Is this pressure going to go up or down if I make the container smaller? Well, we make it smaller. Look at the pressure. It goes up. If we make the container larger, so if we increase the size of the container, the pressure goes down. And so in this situation, as volume goes up, pressure goes down. This is an inverse relationship or an indirect relationship, which means as one goes up, the other one goes down. So pressure and volume have an indirect relationship where as one goes up, the other goes down. So let's go ahead and think of these things as we're going through the notes. All right, so let's go ahead and continue on this exploration of gases, where we are going to talk about the combined gas law, and we're talking about the relationship between pressure, volume, and temperature. This part of the notes is from the last notes. We're going to use the Kelvin scale for everything we do, and again, it's based off of the Celsius scale, but it has no negative temperatures because what it does is it sets absolute 0 to 0. And what you really need to understand from this is that if a problem gives you Celsius, you need to add 273 to convert it to Kelvin. And so in this situation, it becomes 298. Again, if it gives you Celsius, you add 273, and you get 378. And so that's the big thing here. So Just keep that in mind as we do these problems, and I'll point it out when we get there. But if it gives you Celsius, you got to convert it to Kelvin by adding 273. So let's go ahead and talk about the combined gas law. Now we have these three different laws that we're going to talk about: Boyle's law, Charles' law, and Gay-Lussac's law. And what we're going to do is talk about the relationship between pressure, volume, and temperature. And so these laws tell us the effects of changing pressure, volume, temperature, and amount of moles. And so these laws tell us the relationships between those two. Now, the way this table works is that this first part here, these are the constants. And so this is what we are not changing. So if something is constant, that means it doesn't change. So if we have constant temperature and constant moles, then what that means is the temperature and the moles don't change. So the other variables we are talking about are changing. And so this first column here is between pressure and volume. And so I'm going to go ahead and put P and V here because we're talking about pressure and volume, the relationship between pressure and volume. And if you think about it, if you have a container and you make the volume smaller, like you squeeze the volume, you squeeze the container to make the volume smaller, what happens to the pressure on the inside? It increases. And so if pressure is increasing, it's because volume is decreasing. And the opposite is true as well. If you make the volume large, that means the pressure is small. And so we say that pressure and volume are inversely proportional. And another way of saying it is indirectly proportional. That means as one goes up, the other goes down. And the way the graph looks is it looks like this. It looks like this. This is the way the graph looks. If you were to graph volume and pressure, this is the way it would look. And so as volume gets larger this way, notice how the pressure is going down. And as pressure gets larger this way, as it's getting larger, notice how it's when the volume is small. Now the next one we're going to talk about, this one, pressure and moles are held constant. And so what we're talking about is temperature and volume. So we're talking about temperature and volume. And so if you think about a hot air balloon, the temperature, the hot air balloon expands as you heat up the gas inside of the hot air balloon. And so if you increase the temperature of a volume of gas, if temperature increases, volume increases as well. And volume and temperature are said to be directly proportional. And so that means as one goes up, the other one goes up as well. And so the way the graph looks is like this. As one goes up, the other goes up. And then we have volume and moles being held constant in this last one. So volume and moles are held constant. So we're talking about temperature and pressure. All right. And so the volume is constant. And a great way to think about this is imagine you have like a can of hairspray. And you take the can of hairspray, which has a fixed volume. The volume of the can does not change. You take that can of hairspray and you throw it into a fire. What's going to happen to the pressure inside of that can? Well, the fire is causing the can to heat up, and so that means the pressure is also going to heat up. And so what will end up happening is the can of hairspray will increase its pressure, the pressure inside of it, until it explodes. And so in this situation, if temperature increases, that means pressure is increasing as well. Pressure and temperature are directly proportional. As one goes up, the other goes up, and this graph also looks like this. And so these are the relationships. So we want to think about pressure and volume. As you increase the volume, the pressure goes down. As you decrease the volume, the pressure goes up. And then we have temperature and volume. As you increase the temperature, the volume increases as well. That's how hot air balloons work. And then we have pressure and temperature. As you increase the temperature, the pressure inside of a container will increase as well. Now, something to keep in mind is something called standard temperature and pressure. And so we'll talk about this more as we go through, but for the purposes of comparison, scientists have agreed on a standard condition for experiments with gases. And this standard condition is called standard temperature and pressure. And this is the standard temperature, and this is the standard pressure. So that means that if we are at STP, which is standard temperature and pressure, that means the temperature is 273 Kelvin, and the pressure is 1 atmosphere of pressure. And this is really easy to memorize because this is 1 atmosphere. That's pretty straightforward. But the temperature, another way of thinking about it, is 0 degrees Celsius. And so it's 0 degrees Celsius, which is the freezing point of water, in 1 atmosphere of pressure. So keep that in mind as we talk about that. All right, so now what we're going to do is we're going to talk about the combined gas law. And the combined gas law includes everything we know about the relationships between pressure, volume, temperature, and quantity. And this here is the main equation that we're going to be talking about. Now, keep in mind the variables for this. P is pressure, N is moles, and some people might say, why is N moles and not M like Mary? Well, M like Mary is a mass, or meters. V is volume, T is temperature. And so now what 1 and 2 mean, 1 means your initial condition. This is your initial condition. This is what you start off with. And 2 is your final condition. And what this equation is really useful for is if we start with, let's say, a certain pressure or volume or temperature, and let's say the pressure changes, well, if the pressure is changing, it's probably because the temperature is changing or the volume is changing, and we can calculate the new pressure, or I'm sorry, the new volume or the new temperature or the new moles. And so something that we need to keep in mind is that, that when it comes to units, the units you start with have to be the units you end with. So if we're starting with atmospheres as pressure, the units we end with are atmospheres. If we're starting with liters, we're ending with liters. And so all of your 1 variables need to match units with the corresponding 2 variables. So that means, again, if our pressure is atmospheres, that means we're ending with atmospheres. Now this bottom part here says you can start any problem with the combined gas law and cross out the variables that are constant or the ones that are not talked about. And I'm going to give you an example of this here in a moment. And so this here, we are going to use the combined gas law, but these guess boxes are something that we normally use in the year. And so I am going to use this here, but just know that on your daily checks, we're going to be using something different. So it'll look similar, but this is essentially what the guess box stands for. What it stands for, the G stands for given, so what's given to you. The U stands for unknown. The E stands for equation. What equation are we using? The S stands for substitute. That's where we take our givens and we plug it into the equation. And then the last S is solve, where we then solve the problem. And so let's go ahead and take a look at this here. So let's go ahead and read this problem here. It says at a pressure of 405 kilopascals, and real quick, this kPa is a pressure. How do we know it's a pressure? Because it says it right there. It says it's at a pressure of that many kilopascals and a volume of 6 liters. Okay, so we're starting with a pressure and a volume. This is the initial pressure and this is the initial volume. Now it says, assuming the temperature remains constant, that's going to be an important piece of information in a moment here. If the new volume is 4.00 liters, what will the pressure be? And so this is V2. This is volume 2. Now, let's go ahead and write what is given to us. What's given to us is pressure 1 is given to us, and that is 405 kilopascals. Volume 1 is given to us as well, and that is 6.00 liters. And then we have a change in the volume. Volume 2 is going to be 4 liters, 4.00 liters. Now, real quick, let's think about what it's asking for. It says, what will the pressure be? And so it's asking for the new pressure. So what is the new pressure? What will that be? So that is the unknown. Now the equation, this is really easy. We're only talking about one equation at the moment. There will be a moment where we're talking about multiple equations, but right now the only equation we are dealing with is P1V1 over N1T1 equals P2V2 over N2T2. This is the only equation we're dealing with, so that is the equation we use. Now, what we're going to do here is we're actually going to take this equation and we're going to look at what's given to us, and we're going to look at what is not given to us or what remains constant. If something is not given to you, if there's a certain variable that it's not talking about, you can actually cross that out in this equation. Now, this is the only equation you can do this with. You cannot do this with other equations. You can only do it with this one. But notice how the temperature remains constant. And so because it's constant, what we can do is cross out the temperature. So we can cross that out. And what about N? Well, N represents moles. It's not even talking about the moles. So if it's not even talking about it, we can cross that out as well. And notice how when we do that, we end up with this equation here where it is P1V1 equals P2V2. So again, that's the equation that we end up with. So now what we do is we substitute the problem here. Now, P1 is going to be 405, and V1 is going to be 6.00. And P2, well, look, P2 is actually what we're looking for. And so we're just going to write P2, and then V2 is 4.00. And that is the substitute part. Now, the solve part is where you then rearrange the equation to then solve for it. So the way that works is we have 405, 6.00, and how we solve for this is we need to get P2 by itself. Well, how do we get P2 by itself? Well, whatever is happening to P2, you need to do the opposite. Notice how we are multiplying by 4.00. What's the opposite of multiplying by 4.00? Is we are dividing by 4.00. Because when we do that, notice how this cancels, just like units. And then whatever you do to one side, you have to do to the other side. So if we divided the right side by 4.00, we have to divide the, if we divided the right side by 4.00, we have to divide the left side by 4.00. And then what we end up with is this thing here, where we then can take this, type into a calculator, and we end up with P2 is equal to 607.5. Now, what are the units in this situation? Well, remember, the units of pressure that we start with are going to equal the units of pressure that we end with. Well, what units of pressure are we starting with? We're starting with kilopascals, so we're going to end with kilopascals. And so it's 607.5 kilopascals. Now, before we move on, does this make sense? What happened to the pressure? We started out at 405 and we ended at 607. Well, the pressure increased. Does that make sense for the pressure to increase if the volume is decreasing? And the answer is yes, because as you decrease volume, you increase pressure. So that makes sense. All right. Now the next one, if you take a look here, we are given a temperature. So we have T1 is equal to 242. And just to let you know, I'm going through this problem a little bit more quickly now. We also have V1, which is 325. And then it says if the pressure is held constant and the temperature is lowered, okay, so the temperature is being lowered, so this is T2, to 189. The question is, what would the new volume be? So it's asking for the new volume, which is V2. Now again, our equation is the combined gas law here. And again, we can cross out everything that does not, that we're not dealing with or that remains constant. So this is pressures remain constant, so we can cross out pressure like this. And then also it doesn't even talk about the moles again, so we can cross out the moles. And this is the final equation that we're dealing with. And so this is kind of what it looks like. V1 over T1 equals V2 over T2. All right, so now all we need to do is substitute. So we have V1, which is 325, over T1, which is 242. And then we have V2, which V2, this is what we are looking for. We're looking for V2 divided by T2, which is 189. And then the last S is solve. And really to solve this, what you do is you cross multiply this, you cross multiply cross, and then you divide by this. And so when you do that, V2 is equal to 253.82. And again, whatever units of volume we start with will be the units of volume we end with. We started with milliliters, we'll end with milliliters. And again, does this make sense? Well, look at what's happening to temperature. Temperature decreases, and so temperature and volume are directly related, meaning that volume is going to decrease as well. So that makes sense. So if the temperature is decreasing, the volume is decreasing. It's kind of like when it gets really cold in the winter, the tires on your car, the pressure inside the tires go down, and the tire can actually deflate a little bit. And so so yeah, so that's it. So these problems are not too bad. It just comes with practice, and make sure you come to class with questions, and we will go over some more practice problems in class. Have a great day.